Okay, so we continue from where we left this morning. So at the end of the first lecture this morning, we gave a description of this radiation-dominated phase of the early universe. In particular, we assume that the energy density, let's say rho total, is approximately equal to the one stored in radiation, so relativistic degrees of freedom. This is given by this expression. This factor of G star counts the effective number of degrees of freedom with the appropriate statistical factors for fermions and boson. We also show that during this phase, the scale factor goes like the square root of t. So Hubble as a function of t in this phase goes like 1 over 2t, and by using the Friedmann equation, we can find a relation between the temperature of the primordial bath and the time. Okay? And we saw that when the time is equal to 1 second, the temperature is approximately 1 MeV. And if you want to know the age of the universe earlier than that, for example, when the temperature is 1 GeV, it's 1 microsecond, okay? Because you have to take the square of the temperature. So if you add the 3 orders of magnitude in the temperature, you get 6 in the time. And finally, a quantity that I just mentioned this morning, but it will become very, very important for this hour, is the entropy density. So this is the entropy per unit volume. Yes, the units of an energy to the cube, or if you want, the inverse of a volume, because energy and length are the opposite of each other in natural units, and the entropy is dimensionless in natural units, because we said Kb equal to 1, okay? So, of course, this makes sense. We have only relativistic particles. The only energy scale is the temperature, so S must also scale like T cube. For the same reason, rho must be like T to the fourth, okay? So by dimensional analysis, the power of T is very easy to guess. Then these factors are just conventions, and they are defined in such a way that if you consider only photons, these G star functions are just two for the two photons polarization. And then, you know, as we discussed at the very end of the lecture this morning, G star S, they change by a factor of 10 across the entire radiation-dominated history. So we will take G star constant, and of course, if you want to be precise, you can than that, but especially for this hour where we do estimates of dark matter relic density, G star will be a constant, and it will be of the order of 100, okay? Okay, so now we finally get to the point, and the point is dark matter genesis. So how do we produce dark matter in the early universe? So far, I gave you a description, a microscopic description of the primordial bath, but only for the standard model degrees of freedom. I told you that dark matter must be there with an equation of state with W equals 0. Now we start to see what dark matter could be, okay? And in particular, we will discuss production mechanisms of dark matter. Today we will discuss mostly freeze out. If there is time, I will say a few words about freeze in. Tomorrow we will develop the formalism of the Boltzmann equation in the expanding universe, and we will see how to do proper relic density calculations, like with all the numerical details and all the accuracy that we like. The expectation here is that, and we will never use this, but just to give you some context, there are good reasons to believe that the early universe went through an inflationary phase, okay, where the scale factor grew exponentially with time. And then at the end of inflation, we had the so-called reheating. Okay, so for example, the inflaton can decay to bath particles to generate the thermal bath. And starting from this bath, we would like to understand the production of dark matter, okay? And so, a first classification when we discuss about what are the genesis mechanisms, okay? A first classification we can make is between thermal and non-thermal. This is really a zeroth order classification, and I define thermal production of dark matter all the situations where two conditions are satisfied. The first one is that DM, which is the acronym I will use from now on for dark matter was in equilibrium at early times. So you have dark matter coupled to the standard model, to the bath. You go back enough in time, the universe was hotter and denser. Eventually, these interactions between the visible sector and the dark matter were able to make sure that this degree of freedom thermalizes with the bath. Okay, that's the first condition. There is another one. And of course, at some point, dark matter must decouple because the universe dilutes and gets cold. And so thermal equilibrium cannot be ensured anymore. And the second condition is that decoupling is what sets the relic density. Okay? Now, this second point deserves a comment that I will make in a second. Let me complete my classification by saying that I define non-thermal production as anything else, okay? So this is complete, okay? There are no cases I'm missing. So whatever I satisfy these two, I'm doing thermal production. If even one of them is missing, it's automatically non-thermal, okay? So let me give you 3 examples. The first example is freeze out, the one we will discuss today. We will see that these candidates, this class of candidates, are particles that were in thermal equilibrium at early times. Eventually, they decoupled, and the way they decouple is what set the relic density in a way we can compute, okay? And we will see that with details, and even more details tomorrow. An example I could give you where this situation is satisfied, but this one is not, is the so-called asymmetric dark matter, okay? So we know that the omega baryon I mentioned this morning, the 5% of baryons, is a consequence of a primordial asymmetry between particle and antiparticle. So in the early universe, you had baryon and antibaryons with very similar densities, but a tiny, tiny difference between particle and antiparticles. Then you annihilate, you wash out the symmetric component, and this tiny asymmetric component is what survives today. So baryons were in equilibrium in the early universe, they decouple, but the reason why we have 5% has nothing to do with the decoupling. Is this primordial asymmetry. So the situation of asymmetric dark matter is a class of hypothetical theories for dark matter, where the situation is identical to the one of baryons. Okay, you assume, well, you also provide some mechanism to generate this asymmetry. Eventually, you have this asymmetry between particle and antiparticle. Dark matter is in equilibrium. It decouples, but then the relic density has nothing to do with decoupling. The relic density comes from a chemical potential, from this asymmetry, okay? So I already gave you a counterexample why I need both of them, okay? The third situation is anything else, so it's really anything else. The freeze-in case we will discuss at the latest in the last lecture belongs to this class because you don't have one, you don't have two. Dark matter particles produced via freeze-in, they are never in thermal equilibrium, as we will see. Another case is the axion. A axion is something that you will see in much more depth next week, the way dark matter is produced, axion dark matter is produced, okay? So also for the axions, these two hypotheses are not satisfied, and so the axion dark matter is a non-thermal candidate. Okay, so this is the broad classification, and given the importance I'm putting on the concept of thermalization or on being in equilibrium or not, let's discuss how do particles thermalize. Okay? So particle thermalizes because they talk to each other, because there are interactions. Okay? And we can estimate a very naive criterion that works actually very well to see if a particle is in equilibrium or not. Okay? And this is a naive criterion that, as I said, it will work very well, and we will be used until the end of the hour today. Then tomorrow we will develop formally the Boltzmann equation, and we will see that even from the Boltzmann equation we end up with this criterion. And it's not surprising because it can explain in a few simple sentences, and there is a physical reason why this criterion works. But let's start from the beginning. Imagine you have a dark matter particle chi. So chi from now on will be the symbol I will always use for dark matter particles. It doesn't have to be a fermion, it's just a symbol I will use. Okay? So chi can, for example, talk to standard model particles through these annihilation processes. Imagine chi is a Dirac fermion. If it's a Majorana fermion, you will have chi. You have to take into account factors of 2, but the concept is the same. And this SM could be E plus E minus, W plus W minus. Okay, so anything really with standard model final states. These particles, whatever you put here, are in equilibrium. Okay, so if this interaction happens often enough, then dark matter will thermalize with the standard model. So it's interesting to do the following estimate. So to estimate the number of collisions, okay, between T times T1 and T2. Okay, so I wonder how many of these collisions happens between T1 and T2, where T1 is less than T2, of course. Okay, I'm going forward in time. So this is, if I take T1 and T2, close to each other, of course, I'm not combining T1 back at the weak phase transition and T2 today. I'm taking T1 and T2 not too far away from each other. I want to see if thermal equilibrium at that moment is ensured. And I introduce this quantity, gamma. Gamma is the number of interactions per unit time. Okay? So if I have gamma, the number of interactions per unit time, it's a collision rate. Okay? That's what the rate is. A rate is number of events per unit time. The rates as the units of an energy. H bar equal 1. So inverse of time is the same as an energy. So gamma integrating in dt from T1, T2, T1, T2, this is by definition the number of collisions. Okay? So sometimes it's convenient to change variables. So actually let me do so we have seen that there is a connection between time and temperature. Okay? It's written there. So for each time, I can assign a temperature of the bath. So it's sometimes, very often actually, convenient to use the temperature as the evolution variable and not the time. Why? Because these rates are usually known as a function of the temperature in a very simple form. Not surprisingly, because the temperature tells us the typical energy of bath particles, how abundant they are. So it's easy to express rate as a function of temperature. This is gamma chi. As a function of time, the expressions are less obvious, okay? So I just did the change of variable in the integration. So I need to compute this Jacobian, okay? dt, d time over d temperature. And now there is an important concept that, again, it's something that we will use a lot today, tomorrow, and also the day after. The conservation of entropy. So you can show that for a perfect fluid, like the one that is filling the early universe, a fluid of radiation, entropy is conserved, okay? The entropy in a co-moving volume is conserved. So remember, this is S, is the entropy density. So it is conserved only when you multiply it by a cube, okay? And the reason is that a cube tells you how the co-moving volume is scaling with time, okay? So if we also assume, which is good enough for our purposes, G star S constant, as I mentioned, then what we see is that the conservation of entropy corresponds to the requirement that the derivative of temperature times the scale factor is 0, okay? Because look at the expression of the entropy density. S times A cube is a bunch of constant factors times T cube A cube. If TQ A cube is constant, T times A is constant. Let me develop these derivatives, and I find something useful, very, very useful. Because I find dt, d temperature, d time times A plus temperature, dA dt equals 0, Leibniz root for the derivative. And finally, I find that the Jacobian I was looking for is minus h times t. Okay? Going from here to here just requires dividing by a, and you recover the Hubble. Hubble is a dot over a. Okay? Okay, so I can use this, now I can go back to this integral. Okay? I can go back to this integral, and let's see. So when I apply the Jacobian here, I get a minus sign. This minus sign makes sense, because as the time is going forward, the temperature is going down. Because as the universe expands, it gets colder. So what I can do is to say, look, instead of going from T1 to T2, I integrate from T2 to T1. T2 is less than T1. The temperature later is smaller. And then I get gamma H, gamma over H, d log T. Okay? Okay. So now, if I assume that, okay, well, let me move here. Let me move here, because we are about to find the thermalization criterion. Okay, now imagine that you take T1 and T2 not too far away from each other, okay? So you are considered two consecutive moments that are not much far away from each other. So if T1 is not too different from T2, and I call this T, my reference temperature, then I can go back to that integral and say that the number of collisions between, let's say, T2 and T1, T2 is the, well, we can say T1, T2. T1 is larger than T2. Okay, 1 is the first moment and 2 is the second moment. Okay, so I think it's clear, no? T1, the time 1 is the beginning, the time 2 is the end, so the temperature goes down, time grows. Okay, so I can approximate this expression to say, look, if these two temperatures are not too far away from each other, this ratio, gamma over h, is not changing by much, okay? So I can evaluate it. It's an approximation, of course, but you can also take a realistic case. You know how Hubble changes with the temperature. So you can compute gamma and you can try yourself. So you can say, okay, this is gamma over h. I evaluate this at the temperature T. Okay. So I get gamma chi of T over h of T. And then I do the integral, but the integral d log T is just the log of T1 over T2. Okay. So if I take, of course, if I take these two temperatures to be equal, I will get the log of 1, which is 0, which is obvious. There are no collisions between the time and the same time. So I need to take some time interval, which is finite but small. And so this log will be of order 1. Okay. And so I can say that the number of collisions is given by this ratio. Okay. Yes? Where is gamma lambda? These are all chi, sorry. So my handwriting is not the best. Sorry. So gamma chi is the rate, the number of annihilations of this kind per unit time. That's the rate for the annihilations. Okay, so now imagine that you find that this ratio is less than 1. What does it mean? Yeah, sorry. Because these two are very, very close to each other. So if they are close to each other means within a factor of a few, not percent difference. Okay, so this log is an order 1 number. Okay, so if you take, let's take this example, T1 equal to twice T2. So this is actually interesting. Let's take this case. So if you take T1 twice T2, and you remember that T times A is constant, you are taking the amount of time that is needed for the universe to double its size. So that's the time scale of the expansion, okay? So that's the kind of estimate I'm doing. And so log of 2, I'm saying that the log of 2 is more or less an order 1 number, okay? So of course, this is an estimate. We will be more rigorous tomorrow with the Boltzmann equation. But this is just to tell you that this ratio, dimensionless ratio, is a very important quantity for whatever we're doing until the end of these lectures. It's the ratio between the interaction rate and the expansion rate, okay? So if this ratio, now, if you compute this ratio at a given temperature, okay, and you find that this is less than 1, what does it mean? It means that if you take the amount of time the universe takes to double its size, the universe gets twice as big and there are 0 collisions. Well, less than 1, okay? So you can say that chi particles are decoupled. If you find that this is, of course, you would be happier if you have more than 1 collisions, but let's say you need at least 1 to say that the chi particles are coupled. This is a very naive estimate, but it works very well. We will see it works very well tomorrow through the Boltzmann equation analysis, where we can make this derivation more formal. But it makes sense from the physics point of view that this holds, because this is really a competition between 2 time scales, okay? So 1 over Hubble is the characteristic time scale for the expansion of the universe, and 1 over gamma is the amount of time between 2 consecutive collisions, okay? So if the characteristic time scale is much larger than the time between 2 consecutive collisions, it means that a lot of collisions are happening while the universe is experiencing expansion over its time scale, okay? And so it makes sense to say that particles are coupled at that moment. In the opposite regime, of course, the universe doubles its size and nothing happens. And so if particles do not talk, they cannot be in thermal equilibrium. Collisions are central to reach thermal equilibrium. If they don't talk to each other, how can they be in equilibrium? Okay, so this ratio here, which is an inequality between 2 time scales, will be our guideline until the end of this hour to decide if and okay, yeah, also and so this is it will be our guiding principle. If this ratio is larger than 1, then it's coupled. Less than 1, decoupled. When this ratio is equal to 1, well, that's the decoupling moment. Okay? So basically, since we start our discussion from thermal candidates, yes.
Secretly here there is the assumption that there is another coupling that is sort of responsible for the thermal bath to exist.
Oh, you had gauge interactions. Yeah, yeah. So I'm assuming that the standard. You can actually check that in this phase you take a gauge interaction process typical from gauge interaction. You're super safe in that case. Yes, so standard model particles do not decouple because the coupling is weak, but they decouple when they get the Maxwell-Boltzmann suppression. So the couplings are big enough in that case. Well, it shares the temperature if this is true, if they're coupled. Then you can discuss kinetic equilibrium and chemical equilibrium. So to be precise, this is chemical equilibrium because the number changing processes are in equilibrium and the elastic process. But I will discuss this subtlety tomorrow when I do the Boltzmann equation. So for now, let's assume that kinetic and chemical are both essential to be in equilibrium, and that's how we will establish if a particle is in equilibrium or not. Okay. Okay. So I say the division is thermal, non-thermal. We will start from thermal. So for this discussion, dark matter particles are in thermal equilibrium. We want to understand when they decouple. So the decoupling of dark matter, happens at the so-called freeze-out temperature. So I am basically saying that the interactions responsible for keeping everything in equilibrium are freezing out, and this freeze-out temperature is defined from this condition. So when I evaluate gamma and H at Tf, which is the freeze-out temperature, so the subscript F is for freeze-out, when these two rates are equal, that's the moment when they decouple. Okay, so this is also what I like to call and I think I'm not the only one, instantaneous decoupling approximation, because this is a very brutal approximation. We say that for temperatures above Tf, dark matter particles are perfectly coupled, and immediately after, then dark matter particles are completely decoupled. So we treat freeze out as a sudden phenomenon that happens at the given temperature before they are coupled, after they are not coupled. And this is needed if we want to be able to provide estimates like we are doing today. Tomorrow with the Boltzmann equation, we will track the decoupling epoch in details, and we will also be able to discuss when you are not in equilibrium, but you're not too far away from equilibrium. And so particles can still talk without being in equilibrium, but some of this annihilation can happen with an impact on the relic density, okay? But you need a Boltzmann equation for that. Okay, now we do this, and let me explain what I mean by instantaneous decoupling with one equation. So I can tell you that the number density of chi as a function of the temperature is given by number density of chi equilibrium for T greater than Tf. Why is this the case? Because I say that within this approximation, for temperatures larger than TF, dark matter particles are in equilibrium. So I can safely put this, okay? And then here is the key. I can say that if the temperature is below the freeze-out temperature, the number density is the one that freeze out and it doesn't change anymore. Do you agree or not with this expression? You agree? You should not believe everything I tell you. Okay? Sometimes I like to trick people. So this is wrong. Well, above freeze out is equilibrium, below freeze out doesn't change. What is missing? I'm forgetting something very, very important. The expansion of the universe, very good. So this is not correct because even after freeze out, the number density is changing. The universe is getting bigger. The number density is being diluted. Number density, which will motivate the introduction of the comoving number density. But first, let's fix this equation. So this is A. Let me write this as AF over A cube, okay? So AF is the scale factor at freeze out, and this is A, and these are function of the temperature. So you see that there is a volume dilution. So just, I'm not happy about it. Let me write this better. So I have A TF over A of T, okay? So if the temperature is below the freeze-out temperature, there is this price to pay, and this is larger than this, because the universe got bigger. So it's a suppression, it's a number less than 1. It's a dilution. Okay, so why did I care about this? Well, this equation, first of all, defines the instantaneous decoupling approximation. This is what I mean by instantaneous decoupling. So this blackboard is the summary of everything else we will do today. I'm assuming a particle is coupled. I take the decoupling temperature when gamma and h are equal, and this is the solution for number density, period. But this blackboard is telling me that n chi is not the good variable, because in the end, I want to scale out the effect of the expansion. That's a boring effect that I can understand very well. Once collisions stop happening, I would like to stop worrying about what happens. And so this motivates the introduction of the so-called comoving density, which I will explain in a second. Okay, the comoving number density is defined as follows. Comoving number density. Okay, so the comoving number density is defined in this way. Y, chi, it's a symbol I use for the comoving number density, is the number density divided by the entropy density. Why is this a good quantity? Because this quantity doesn't change. So if I write now the equivalent of this equation here, then I can really do what I was trying to do before. I have y chi ec t for t greater than tf, and then I do really have y chi of tf here when t, so you see, much simpler. And the reason why I like this variable is because as soon as I got to freeze out, I can stop worrying about anything. In particular, the y chi today, when I put here the current temperature, this is equal to the freeze out value, because nothing else happened. The reason why this is true is that there is a simple way to see that. You can write this in this form. After freeze out, the numerator is constant. because it's only dilution effect. And the denominator is, of course, constant because entropy is conserved. So after freeze out, this ratio is constant. Okay? So this is really the variable we want to use. And it's also, now we are almost ready to do the first relic density calculation. But before I do the first relic density calculation, let me tell you how we compute the dark matter density. On the one hand, there is the measure value, which is 0.12. Of course, there are other digits. If you look at the paper, for example, from the Planck collaboration, there is a 0 here. Okay. It's measured with very high precision. Okay. Sorry. Important h² factor. Okay, so how do I measure? So this is omega dm h². This is an observational value. If I am a theorist working on a dark matter model and I want to compute the equivalent of that and see if they match, what do? I say, okay, omega chi h². So this is the observed value, this is the predicted value. The predicted value is omega chi today divided by, let me be precise because this is omega critical today divided by h². Omega critical today is the number we saw this morning. Remember, the very small density. How do I compute the energy density today? The energy density today, this is cold stuff. No kinetic energy whatsoever. W equals 0. They are at rest. The energy density is mass times the number density. Okay? So it is mass times number density. Of course, both, no, well, the mass evaluated, it's constant. I'm assuming the mass constant. The number density evaluated today. So doing a relic density calculation and see if the predicted value matched the observed value, well, then requires to compute the number density of dark matter today. Okay? And the number density of dark matter today, this variable here, that's the only thing I don't know, okay? If I have a model, the mass is a parameter of the model. I can, of course, change it to see how it depends on the mass. We will see how it does not depend on the mass today. But n chi is the prediction I have to make. And the proper way is to do the Boltzmann equation. But if you want to do an estimate, well, the estimate is simple because I think you would agree with this, no? The number density is the comoving density times the entropy density. It says by definition. Y is n over s. So n is y times s. But then, the number density, the comoving number density, is equal to the one at freeze out. Okay? So in this equation, I have a quantity S of T0. This is a number that we know it, 2,891.2 centimeter to the minus 3. This is the entropy of the universe, okay, today. You can compute it. You have the equation, you compute all the G star. You have to account for the fact that neutrinos have a different temperatures than photons, but it's something we can do, okay? And so everything is known with the only exception of this. So you see, if I manage to understand the value of this, then I use this equation here with the known value of the entropy density. I plug this here, and I have a prediction for the relic density. And this prediction at least has to be smaller than the observed value, okay? If I find omega chi h² less than 0.12, it's fine. It just means this is a subdominant dark matter component. It's not ideal, of course, because all the experimental rates will be suppressed by the ratio of the density, the fractional contribution to the density. But it's okay, it's acceptable. If this number ends up being more than 0.12, then you are excluded because you cannot produce more than what you observe. Okay? Okay, so you see that from this blackboard here, first of all, how useful co-moving quantities are in this context, and also the essential role of this quantity here. So in the remaining 45 minutes, we will do calculations of this, and then we will plug these calculations here. Okay? Questions? Yeah. For warm, you have to do a separate calculation, but it cannot be too warm. I will get to warmness if I have time in the last lecture when I do freeze-in. But for now, let's just say that kinetic energy is negligible. So it's really cold. It could have some degree of warmness, but then structural formations put severe bounds. So it's, for now, let's say it's cold. Okay, so we are ready to do the first relic calculation. And so we are ready to do and compute what is called the relic density of cold dark matter. But before actually, let's spend only one blackboard on this, okay? Say cold versus hot relics. So why? So the question is, what is the relation between TF and MKI? Okay, so in other words, when dark matter decouples, it's relativistic or not? Okay. We will focus in this lecture. We will do the complete estimate with all the factors, and we will go through the calculation well. We will do this for the situation where TF is less than MKI. Okay, so for the so-called cold relics. But it's important to spend a few words about hot relics, particles that decouple when the temperature is much larger than the mass. Why is this important? Any idea? Any known candidate that has this? The neutrinos, so they exist for sure, okay? They exist, they decouple the MeV scale. You can get this number actually by the gamma over H. You know, you put the powers of the Fermi constant, power of temperature, you recover the MeV very easily. The MeV is way bigger than the neutrino mass, okay? And so the neutrino, so for, let's say, standard model active neutrinos. So by standard model active neutrinos, I really mean the component of the weak doublets, left-handed components, okay, no sterile singlets. So for these kind of particles, the decoupling happens when TF actually much, much larger than the neutrino mass, okay? But of course, neutrinos are there, neutrino decouple, and neutrino contribute to a fraction of dark matter, okay? So you can do a calculation that maybe we can sketch at the end of the hour if there is time, but I really want to get to the cold relics because it's what is interesting to us. But you can do a hot relic, actually it's much easier for the hot, but you can compute how the neutrino relic density depends on the mass. And you see that to reproduce the observed abundance for neutrinos, you need a mass way above the terrestrial bounds, okay? So this is one of the reasons. Dark matter. There are other reasons now. Historically, this is an important example, but neutrinos cannot be dark matter. These standard model active neutrinos, I'm not talking about the sterile. First of all, because the relic density fails, you need a mass of 10 electron volt in this range. And you know, from experiments such as scattering, the mass bound is below that. Then you have structure formation bounds. These are hot candidates, and you have free streaming lengths that erase cosmological perturbations too much to be tolerated. And the third reason is the Tremaine-Gunn bound, which is a bound on fermionic dark matter from statistical mechanics consideration. Basically, you cannot squeeze fermions too much because they cannot occupy the same state. And this is a bound, it depends on the system you observe, but this bound says that the mass of the fermionic candidate must be greater than roughly 1 keV, okay? Then, of course, we can discuss about the first digit or the precise, but that's the order of magnitude, okay? So neutrinos is, well, it's important because they are there and they provide a subdominant component. They are one example of hot relics, and they're not able to explain 100% of dark matter. So in general, hot relics cannot explain dark matter. Let's say I will say a few words about free streaming again if there is time when I do freeze-in, but not only neutrinos fail, but even hot candidates are not able to account for 100% of dark matter. So the good or bad news is that if neutrinos do not work, we need physics beyond the standard model, okay? So we need to look for something else. And whatever we look for must be cold, okay? So let's now compute the relic density of cold relics. Okay? So now we do the first calculation of relic density, and we will end up putting the right numbers here and finding out omega chi h square depends on the parameter of the theory. So what are the parameters? Particle physics. So the particle physics properties that have an impact on the relic density are the dark matter mass, m chi, okay, which is already appearing in this equation here, okay? And then there is, of course, the annihilation cross-section. Actually, it's not really the cross-section, it's the cross-section times the relative velocity, technically speaking, the Muller velocity. We will see more about that. But, you know, to discuss thermalization, we don't care about cross-sections, we care about rates, okay? And the rate is number density, sigma, times relative velocity. It depends also on the relative velocity. Interaction rates of the collisions I mentioned before, because we want to investigate the decoupling. So let me say that the quantity that matters here is the thermal average of sigma v. Why thermal average? Because when I compute the rate, dark matter as a distribution is in equilibrium. So I'm assuming it's in equilibrium, and then I'm investigating when it decouples. But while it is in equilibrium, I have to average for all the possible incoming states, all the possible directions, all the possible energy. So we will define this quantity tomorrow, okay? And, you know, since we will evaluate this quantity in the non-relativistic limit, when the energy of the dark matter particles is less than the mass, because the temperature is the mass. So in other words, V is much less than the speed of light. It will not be so much less, but it's so, of course, this approximation is not needed. You can also keep the full velocity, but just to introduce you to this well-established technique. So you can take the combination sigma v and you can expand in partial waves. This is the S wave, P, D, F waves, okay? So we do no relativistic scattering in quantum mechanics. And if you want to get an order of magnitude, it's important, it's enough to keep the first piece. It's often the S-wave contribution, not always. Sometimes this happens in some specific framework. This is usually present. But now, given the extreme precision, you see, this is really a number precise with a very high accuracy. So this is not needed, okay? This is something that you can actually keep all the orders in V. So you just compute sigma in the way you do like in QFT textbooks, and you don't make any approximation, okay? For this estimate that I do now, I will set sigma times V equals to a constant, okay? So we are doing an estimate. I'm assuming to work in a model where the S wave contribution is there. And I call this S contribution sigma 0. Of course, the average of a constant is the constant itself. Okay, so I don't need to do any average procedure. Okay, so this is the setup. And now we can start to investigate the decoupling. I will do it immediately, because in the end, to study the decoupling condition, what I really need is to compare the Hubble rate with the interaction rate. The interaction rate is not the cross-section. The interaction rate is the number of targets times the cross-section times the relative velocity. And so that's why there is this additional factor of V. So I will write now, that was really the next item on the list. Okay, so let's say computing is too strong. Let's say estimates of TF. So how do I estimate the freeze-out temperature? By the time I estimate the freeze-out temperature, I'm done, because then the comoving density is constant. I have all the equations I wrote before, so I know the Rayleigh density. So the estimates of TF, it goes back to okay, so the collision rate is the number density, number of targets. Remember, it's chi bar. So the number density of dark matter is also the number of targets, times sigma 0, which is this combination sigma V. The reason why I call it sigma is that V is dimensionless in natural units, so this combination is a cross-section, okay? So this is the collision rate. Yes? Sorry? Oh yeah, but this is an estimate. Well, actually, no. The annihilation process is chi against chi bar. So you can put the number density of chi bar here and put all the numerical factors precisely. Of course, this is an estimate where we already gave up a factor of 2 of precision, okay? But yeah, so if the Dirac fermion is a candidate, in this case, you have particles and antiparticles. So when you compute this, even though it's a Dirac fermion, you put for the number of internal degrees of freedom 2 and not 4, because it's precisely, if you are a particle, you can only annihilate with an antiparticle and not with the particle itself. So these numbers can be taken into account. Sigma 0 is this. And then Hubble is pi square root of G star TF 3 square root of 10 TF squared and Planck. Hubble at freeze out. Okay? This is the Friedman equation once I plug for rho the energy density of radiation. Question? Sorry? Yeah, if you want, yes. If you want, yes. We will in the end we will put this equal to this, so we will forget about Hubble. It's a number, function of TF. There is something that we still don't know, because given the information I gave you this morning, I only gave you the expression for the number density in the relativistic regime. You remember? I told you I take, and by the way, of course, I am allowed to put the equilibrium symbol here because by assumption, I am in equilibrium until freeze out. So that's the last moment when I'm allowed to use this. And the number density of a particle with temperature less than the mass, remember, TF is less than mchi, okay? So this is really something we haven't seen yet. So as an exercise, you can check and you can recover something that should be already familiar, which is this very famous result. Okay, so times, well, put the sigma 0 here, okay? So it's a sigma 0 times, what is this? This is the Maxwell-Boltzmann number density, okay? So the 2 pi factors are the usual ones, mkitf to the 3 over 2. You see they also get the right dimensions because it's an energy cube. And then you have this very famous exponential suppression, okay? So, and this is something you can check trivially by doing the integral of the phase space distribution, but you have to take the Maxwell-Boltzmann distribution and then No. Where do we use radiation? Here. Good. So the energy density is dominated by radiation. Dark matter is one particle which is contributing with a very, very tiny fraction to the total energy density. So here I have to put the energy density of radiation. But here, the number of targets is number target of dark matter particles. So I have to put this Maxwell-Boltzmann suppressed. Okay? Okay, and let me also introduce this quantity, which is the dimensionless freeze-out temperature, xf. It's m over t, okay? Which is basically what appears in the exponential. Yes? Sorry? Is it clear now? Was this the question? Yeah. Why? Why is it dimensional correct? Good. Let's do the dimensional analysis. Gamma, interaction rate, energy to the first power. Nchi, number density, energy to the cube. Cross-section, energy to the minus 2. Okay? 3 minus 2, 1. Okay? So, dimensional is correct. Other questions? Okay, so let's solve for the freeze-out condition. So the freeze-out condition now can be written as follows. We have sigma 0, g chi, then we have m chi cube over 2 pi to the 3/2 times xf to the minus 3/2 e to the minus xf. So you see, this is the gamma. The gamma is expressed in this form because I'm using x instead of t. X is dimensionless. So again, the dimensions works. 3 minus 2, 1. Okay. And then for Hubble, I have pi square root of g star. It's understood that G star is evaluated at TF. I will not repeat that every time. Then I have m chi squared over m Planck xf to the minus 2. That's the freeze-out equation. okay? And the freeze-out equation can be solved, okay, numerically. Imagine you have your model. You have a mass, you have a Lagrangian, you use the Lagrangian to compute the cross-section. If you want, you do the thermal average, but then you can get this number sigma 0. G chi depends on the candidate you have, but you know everything. You know M Planck. The only unknown quantity in this equation is what? Is xf, okay? So you cannot solve this analytically because xf appears both as a power law as an argument of the exponential function. So you cannot solve it analytically, but we can do something to gain some hint. Of course, if you give this to a computer, you immediately find a solution. But it's nice to understand what kind of XF we are talking about. Of course, XF must be greater than 1. Look at the definition. If XF is smaller than 1, what we are doing is not self-consistent. Because we assume that XF was greater than 1 to write down the Maxwell-Boltzmann distribution. Okay? So we solve for this, and then we make sure XF is greater than 1. Otherwise, we have to go back and revisit the assumption. Okay? Okay. So let me do some simplification. So I bring all the XF dependence on the left-hand side. So I have e to the XF, XF to the minus 1/2 equal. Okay, now let's be realistic and let's not pretend to keep track of all the pi factors. But what I really want to focus on is on the dependence of this right-hand side of the quantity with physical dimensions. Okay, so I have m chi, m Planck, sigma 0. This constant here, of course, is something that you can compute. Let's call this alpha, okay? No, alpha is a gamma, okay? Gamma is a constant. It's a constant that would depend on g chi, 2 pi, square root of 10. The g star, of course, is also part of it. But you see, in this equation, there are no crazy big numbers. There are no numbers like 10 to a huge power, okay? These are all numbers that are more or less under control. And so we can take the log of both sides. And then from this equation, we get xf. It's 1/2 log of xf plus log of gamma plus log of m Planck, m chi, sigma 0. Okay? So that's the equation that will give me the freeze-out condition. Okay? So you can imagine, so far I haven't made any approximation. Okay? So far I took this one and just worked through it. Imagine that gamma is something that I can identify. Okay? Now, I could solve this either by iteration, or I can try to see this, okay? Because this gamma is not a huge number. Once I take the log, it will not be something that bothers me a lot. But this one is some interesting dimensionless combination, okay? So I want to understand what are the typical values I should expect from this number, okay? So now we will put explicit numbers here, and we see what we find, okay? And then if we find that this is a number which is 10, 20, 30, then these are totally negligible, okay? Because they're both suppressed by a log, okay? Okay, so let's do this. And to do this, we need to specify some typical numbers. We need to specify some typical numbers. And I will do this calculation by choosing a benchmark, which is the benchmark of weakly interactive massive particles, the benchmark of WIMPs. But, you know, even if I move the mass by a couple of orders of magnitude, there is a very small sensitivity. It's a log sensitivity. So if I change the mass by a factor of 100, XF will suffer the appropriate amount rescaled by the log. Okay, so it's not gonna change by too much. Okay, but let's focus on a WIMP benchmark to see the explicit value. So the WIMP benchmark that I choose is MChI of the order of the weak scale, okay, mass of 100 GeV. And then the annihilation cross-section, I take 1 picobarn, okay? 1 picobarn size by the weak interactions. Okay, now M Planck, we saw it this morning, 10 to the 18 GeV. So this combination, this times this times this, is dimensionless. It's the argument of a log, so it better be dimensionless. But of course, if I want to make it in a dimensionless form, I need to remember what a picobarn is and how to do conversion, okay? So first of all, 1 picobarn is 10 to the minus 12 barn, and 1 barn is 10 to the minus 24 centimeters squared, okay? So 1 picobarn is 10 to the minus 36 centimeters square, okay? But it's still not enough. It's not enough because I need to find a way to bring this into GeV to the minus 2, okay? And how do I do that? I remember that in natural units, this combination, H bar C, which is 197 MeV times Fermi, if I compute it with the numbers from the international system and I convert the energy in joule into MeV, this is equal to 1, because both H bar and C are equal to 1. Okay? So now I will use this equation to convert the cross-section into GeV to the minus 2. Okay? So I'll do the calculation in real time, so check for mistakes. And this time the mistakes will not be on purpose like before, okay? They will be honest mistakes. So 1 is, let's say, 0.2. So the first approximation is 1, 9.7 is 2. GeV, okay? 197, so 1 GeV is 8,000 MeV. It's working, okay. 1 Fermi is 10 to the minus 15 meters, or 30. Okay. So let me also, well, let's keep the 2. Let's keep the 2. Let's keep the 2. 10 to the minus 14 GeV times centimeter. This is 1. Okay. So now I go back to sigma 0. Sigma 0 in my benchmark is 10 to the minus 36 centimeter squared. So 1 centimeter is 1 over 2 times 10 to the minus 14 GeV squared. Okay. So instead of the centimeter, I use this equation to do the conversion. Okay, now it's quite trivial. I get 1 over 4. Then, so this 1 over 4 is 1/2 squared. Minus 20, minus 14, plus 14 here. 28, 36, 8. Okay? Which is also 2.5 times 10 to the minus 9 GeV to the minus 2. So this is what 1 picobarn is. Okay? So if you try to parenthesis, let's say parenthesis, if you plug for sigma 0 this expression where alpha is 10 to the minus 2, it's a fine structure constant for weak interactions. 32 pi is phase space, just to count carefully, and you put here the weak scale, that's the number you get. Okay, that's why These are known WIMPs. Originally, they were hypothetical particles with SU2 cross U1 interactions. So they got a bit extended. Now WIMPs is really anything cross-section of this kind, but the origin of the name WIMPs, the W historically really meant charge under SU2 cross U1, the gauge group, the weak electroweak of the standard model. And some WIMPs more broadly now, just weak scale candidates with weak scale cross-section. Okay, so let's go here. Let's compute XF. Let's compute XF. Once we have XF, is easy to get to the final number. So I go here, XF 1/2 logs XF plus log gamma plus log, and now I put the numbers, okay? So 10 to the 2 GeV. This is a dark matter mass, hundreds of GeV. Planck mass, 2.4 times 10 to the 18 GeV. And then the cross section is 2.5 times 10 to the minus 9 GeV to the minus 2. Okay, so please forgive me about the argument of this log going on 2 lines. Okay, but this is really a product of, okay. Very good. 1/2 log of XF, log gamma. Now let's see what is left over here, because GeV to the minus 2 go away. Nice. So log dimensions are gone. So I have this 2.5 times 2.4, let's call it a 10. Okay? 2. Okay. So I get 10 from this. 10 square plus 1, 10 cube. 3 plus 1, 18 is 21. 21 minus 9 is 14. Okay? Sorry, minus 9 is 12. 12, sorry. There is a log, so it doesn't matter. So without the log, it would have been... Okay, so what is the log of 10 to the 12? This is 12 times the log of 10, which is more or less 25. Okay, this is a very famous number. Okay, so this 25 is really what sets the freeze-out temperature for this class of candidates with width scale mass and cross-section. And you see, I'm missing this. But if I put if I solve this equation through iteration, and I put this back, this solution, log of 25 is not a big correction, so it converges pretty fast, okay? So this first estimate I did, it works actually very well, okay? And so we found that for weak scale mass and weak scale cross-section, dark matter particle freeze out when the temperature is equal to the mass over 25, so less than the mass, and this is self-consistent with the assumption of being of having cold relics. Okay. Keep in mind what I said already. If the dark matter mass is not around the 100 GeV, even if it's 1 GeV, if the cross section changes by a factor of 10 or 100, are minor perturbations to the freeze out temperature. So the freeze out temperature depends very weakly, and by weakly I mean logarithmically, on the mass and on the cross section. Okay? So this 25 is quite robust if you don't move away from that benchmark. We will see now that we are going to compute the relic density, and the relic density will still depend very weakly on the mass, but it will have a more prominent dependence with the cross section. But that's what we are about to do. Okay? Okay. Okay, so now that we have the freeze-out temperature, we are basically done, because all we have to do is to, and here there is a, it's important to do things in a clever way here. It's easy to get lost in the calculation if you don't think about what we're doing, because remember, I need to know what? I need to know y chi at the freeze out, okay? I need to know this. So if you start from the definition, we give up immediately. Because you can do, say, okay, then you say this is g chi m chi tf over 2 pi 3 over 2 m chi tf over 2 pi square over 45 g star s tf cube 45. This is the definition. You see that you could try to put 25 here, of course. I want to keep as much as possible the explicit dependence on the mass and on the cross-section. So I want to use this expression for the XF, okay? So what is a more convenient way of doing things? So we have no much, so this is not the best way, okay? Even though it's a definition. There is no much freedom on choosing the denominator. And the reason is that the denominator is the entropy density at the freeze out. But for numerator, we can do something clever. And let's revisit the freeze out condition. The freeze out condition is n chi tf sigma 0 equal h tf. This is where equilibrium, of course. This is where we started from, okay? This is the freeze out condition. So if I want to know, let me rewrite it here. So I use this, and so y chi is n chi equilibrium over s. And then what I do, I take n chi from here. So I immediately avoid dealing with the exponential factors here. Everything is a power law. Wrong. The one I was doing before was not wrong, just as convenient. So I do this, so I have h tf divided by sigma 0 s tf. Very easy. No reason to deal with exponentials, okay? The freeze out condition tells me what n chi is. And it tells me this in terms of h and on sigma 0. Okay, now I have to replace the explicit value for Hubble, for the entropy. So let's do this with patience. So I have 1 over sigma 0. And you see already that sigma 0 is in the denominator. We will discuss this in a second. Then we have 1 over 2 pi square over 45 g star s tf cube. And then you have Hubble. Okay, that's the expression. We are almost done. Remember, once we have TF, we go back to the previous equation, we have immediately the dark matter Rayleigh density today. Okay, so that's just a piece of information that we need. We have 10 minutes. We'll get to the end. So, up to numerical factors that of course, we can track, but it's not really the important point here. From this equation, y chi equilibrium at the freeze out time is what? Is 1 over sigma 0. If you want, keep track of the G star dependence. It's interesting that there is the square root of G star divided by G star x. And now the most important part is this, is 1 over TF and Planck. Okay. Okay. So what I do is I take this equation and I multiply this by the mass of the dark matter. So I have m chi, y chi TF, equilibrium. This is what? This is 1 over sigma 0, square root of G star S. I'm neglecting of pi factors. Possible to keep track of them, but I want to focus on the important part. Then once I multiply this by m chi, I have m chi over TF. That's XF. Okay? So this is the final equation. Why this? Oh, Planck. Very important, and Planck. And also dimension is important because this has mass dimension 1. Mass times something dimensionless. So you get energy to the +1 in the right-hand side. So you see that this combination here, m times y chi, it's important because y chi equilibrium TF is also m chi y chi today. Remember, the co-moving number density doesn't change after freeze out. And so I have m chi, n chi today, S of T0, and this is basically rho chi today. So the combination I put in the box up to a multiplicative constant, which is the entropy density today, is the dark matter density today. Okay? So the dark matter density today depends on m Planck, of course. The m Planck fields m Planck, like the interaction, the expansion rate depends on m Planck. 1 sigma 0. This dependence is interesting. What does it mean? It means that if the cross section is large, the relic density is smaller. Okay? If you increase the cross section, you end up with a smaller relic density. Why does it happen? So you have to imagine that the dark matter particles are in the Maxwell-Boltzmann tail, the exponential tail of the distribution. And the longer you wait, the more this Maxwell-Boltzmann suppression will be severe. Okay? So if you push the decoupling temperature later, you experience more Maxwell-Boltzmann suppression, which means a smaller relic density in the end. And how do you delay the freeze out? By increasing the cross section. If you increase the cross section, if you increase the way particles interact, you stay coupled for longer. Okay? So this cross section appearing in the denominator makes a lot of sense. Okay? It's just telling you that the longer you stay in equilibrium, the more suppressed. Okay? And then there is this XF. Remember, XF is the log of XF. Sorry, XF, the log of M chi, M Planck, and sigma 0. So it's not true that the relic density the mass. There is a small mass dependence, but the leading dependence is on the interaction strength. And if you assume that this particle exists and they thermalize, they need to interact strongly enough in order to make sure that you do not overproduce dark matter. If you make this sigma 0 small, then this quantity maybe goes above the observed value. Okay, so there is a minimal interaction strength that is needed in order to not overproduce the dark matter. So which one, sorry? Yes, sorry. Thank you. Yes. It was a constant, so no, but you're absolutely right. The co-moving number density is n over s, exactly. Thank you. Okay, so to conclude, let me give you this is the equation in the way that it's usually written. You can see that the omega h square is 0.1, okay? Then you can put square root of G star over G star S divided by the square root of 100, more or less. So you combination equal to 1 if you evaluate that high temperature. It's 100 square. Then you have XF, which is normalized to 25, which is the number that we just computed. And then you have 1 picobarn over sigma V. Okay, so that's basically the same equation I wrote. And from going to here, I had to divide this by the critical density, okay? So if you do this, and you see, now we understood the dependence. We understood that the mass appears through this XF dependence, so there is a tiny dependence on the mass, which is log. Cross-section appears in the denominator, but then we need to understand what kind of cross-section we are talking about. And the reason why before in my benchmark I took 1 picobarn is because 1 picobarn is precisely what you need. Remember, the observed value is 0.12, okay? So sometimes which is an expression I don't like, but people talk about the WIMP miracle. I don't like this for several reasons, but well, let me tell you some of them. What?
At some point it was a miracle.
It's not a miracle, it's a coincidence. It's a coincidence. So this is equal to 1 picobarn. It's equal to 1 picobarn because you put this to the weak scale, and this to weak scale coupling, weak scale mass. But of course, if you take a smaller mass, all it takes is a smaller coupling. We know that, right? So it doesn't have to. You don't need to have any. You don't need to have any. Have good motivation. We have motivations to believe that physics must be present at the weak scale. There is a nice way to understand this miracle, and I will put this derivation in the notes, and you can ask me in private, but since I have 1 minute left, I will just give you this magic equation. This is really not a miracle, it's a coincidence. So if you take the geometric mean of the Planck mass and the matter equation, matter radiation equality temperature in GV, the Planck mass, this equality, when you finish the radiation emitted, it's of you take the geometric mean of it, and you get the weak scale, okay? So this calculation here can be understood, can be imposed as a condition on this. It's it is what it is. So actually, I think it's sorry, it's mw over alpha. It's m alpha. It's a bit more than the weak scale, okay? Because this factor is 10 to the minus 2, okay? So you see, alpha over mw is the combination that enters the cross section. Is what is fixed to reproduce the relic density. So this is markable. The two mean very close to the weak scale. Okay. I will stop here with this equation, which is the result for the relic density of cold relics, and we will derive this again tomorrow with the Boltzmann equation. Okay. You can put all the precise numbers, but at this level, I meant 0.1. If you keep track of all the numerical factors, you can be more precise. But at this level, I just meant the order of magnitude. No, he was asking. He was asking if I normalize this to 0. just pinpoint the order of magnitude. Okay.
And in the expression, we have a logarithmic dependence of the m chi. So if we increase m chi, let's say enormously, we have a logarithmical increase of the xf, but it's a bit counterintuitive, isn't it? Because higher the m chi, we expect a lower xf.
Sorry, higher MKI, you expect large, but this is the, remember, XF is the ratio between mass and temperature. It's not an overall scale of the time, it's a ratio, so be careful when you try to make this extrapolation. Of course, MKI, well, there is no time to talk about, maybe tomorrow. There is the unitarity bound that tells you that MKI should be less than 100 TeV roughly. So we cannot increase this as much as we like if we want this framework to be consistent. Then you can go beyond, of course. But
There are more questions. Let's thank Francesco again.
thank you.